Session 2 is prerequisite. This section discusses 3 prerequisites. First, we explain how to create boundary conditions and name selections in various CAD software. Next, we address conformal and non-conformal meshing, demonstrating how to create new parts in Design Modeler and use SpaceClaim's shear topology. Finally, we address mesh quality. Before we dive into the specifics of creating boundary conditions and name selections in your CAD software, let's understand why this crucial step is essential for successful fluent meshing. Properly defining boundary conditions tells Fluent where your fluid domain begins and ends, specifying the physical properties and interactions at those boundaries, like inlets, outlets, walls, and symmetry planes. Accurate name selections allow you to easily assign these defined boundaries to your mesh in Fluent, ensuring that your simulation accurately reflects the physical reality of your model. Without correctly defined boundary conditions and name selections, your Fluent simulation will produce inaccurate and unreliable results. In this section, we teach how to create name selections in Design Modeler, SpaceClaim, and ANSYS Discovery. This is a 2D geometry in the Design Modeler, and we want to create name selections for it. First, select an edge. Then right-click and choose Name Selection. Click on Apply and enter the name Inlet. After that, click on Generate. Next, select another edge. Right-click, choose Name Selection. Click on Apply and enter the name Outlet. Click on Generate again. Then, select 3 edges which form a wall. Right-click, choose Name Selection. Click on Apply and enter the name Wall for the boundary condition. Click on Generate. Finally, to create the flow domain, select the body or surface. Right-click, choose Name Selection, click on Apply, and enter the name Flow for this domain. Click on Generate to complete the process. I want to show another example of name selection, and this is a 3D model. First, select the inlet surface. Right-click and choose Name Selection. Click on Apply and enter the name Inlet. Then click on Generate. Next, select the outlet surface, right-click and choose Name Selection. Click on Apply and enter the name Outlet. Click on Generate. After that, select the fluid body domain. Right-click and choose Name Selection. Click on Apply and enter the name Flow Zone. For the solid boundary condition, select the solid domain. Right-click and choose Name Selection. Click on Apply and enter the name Solid Zone. Finally, click on Generate. All name selections are now complete. Here's how to create name selections in SpaceClaim software. This is a 3D cylinder model. At first, choose the Select command and select the inlet surface. After that, go to Groups. Click on Create NS and insert the inlet name. After that, select the wall surface. Click on Create NS and insert the name Wall. Return to the geometry, select the outlet surface, click on Create NS, and insert the outlet name. Finally, triple-click to select the entire body, click on Create NS, and input the name Flow. Now the name selection for the cylinder is complete. In ANSYS Discovery, we can create name selections. For example, here we have a 3D cylinder. We select this face, go to the name selection, create a name selection, and insert a name. For example, inlet. Next, select another surface, create a name selection, and insert the name wall. Return the geometry, select the outlet face, click on Create a Name Selection for selected object, and insert the name Outlet. After that, we can triple-click on this body to select the entire body. And again go to Name Selection and insert the name Flow. Now our name selection in ANSYS Discovery is completed.
In this section, we discuss the steps required in CAD software such as Design Modeler, SpaceClaim, and ANSYS Discovery for generating conformal or non-conformal meshes. We accomplish this purpose by using Form New Part in Design Modeler and Share Topology in SpaceClaim and Discovery. Conformal and non-conformal meshes represent two distinct approaches to handling interfaces between regions with different mesh densities in ANSYS Fluent simulations. As illustrated in this example, we have two regions with significantly different face sizes. Region 1 with 0.1 meter elements and Region 2 with 0.1 meter elements. In the conformal mesh, bottom left, elements gradually transition at the interface, ensuring nodes align perfectly between regions through progressive refinement. Notice how the mesh gradually adapts from fine to coarse while maintaining connectivity. Conversely, the non-conformal mesh, bottom right, maintains distinct element sizes right up to the boundary, creating a clear discontinuity where nodes don't match across the interface. During simulation, Fluent handles this non-matching boundary through interpolation algorithms. Each approach offers distinct advantages. Conformal meshes typically provide higher accuracy at interfaces, but require more complex meshing techniques, while non-conformal meshes simplify the meshing process and are particularly useful for sliding interfaces, rotating components, or when preserving specific mesh characteristics in different domains is essential. As you know, this is Design Modeler software. You can see that we have two bodies, a bigger cylinder and a smaller cylinder. If we hide the small cylinder, you can see we've subtracted the small cylinder from the big cylinder. We right-click in the monitor of the software and select Show All Bodies. Now we want to create new parts, so we select both bodies, right-click on them, and select Form New Part. Now our geometry is ready for generating a conformal mesh. Now we want to perform a share topology operation in SpaceClaim software. It's a similar geometry to what we used in Design Modeler. We hide the small cylinder so you can see the geometry clearly. There are several ways to prepare the geometry for generating a conformal mesh. First, we select both bodies. Right-click on them and select Move to New Component. In the Share Topology panel, we change the None to Share. In the second approach, we can change the None to Merge. The third way to prepare a geometry for conformal meshing is to go to the workbench and select Share. Then click Complete. Finally, for complex geometries, we can use Force Share. Additionally, if you want to unshare the bodies, we can use the Unshare option.
Different types of mesh in fluent meshing. In this section, we'll explore the 4 primary mesh types available in ANSYS Fluent's meshing workflow. Each mesh type has distinct characteristics that make it suitable for different simulation requirements. On the right side, you can see the Fluent Meshing workflow panel, where you can select these different mesh types when generating your volume mesh. The choice depends on your specific simulation requirements, geometry complexity, and computational resources. Polyhedra. At the top, we see a polyhedral mesh, characterized by cell elements with multiple faces. Polyhedral meshes offer an excellent balance between accuracy and computational efficiency. They require fewer cells than tetrahedral meshes for comparable accuracy and provide better solution stability. Polyhexcore. The second example shows a polyhexcore mesh, which combines hexahedral cells in the core region with polyhedral cells in transition areas. This hybrid approach maintains the efficiency of structured hexahedral elements in bulk flow regions while leveraging polyhedral elements' adaptability near boundaries and complex geometries. Hexcore third is the hexcore mesh, featuring primarily hexahedral, cube-like elements in the core flow region with tetrahedral elements near boundaries. Hexahedral elements are computationally efficient and provide high accuracy, especially when aligned with the flow direction. Tetrahedral. At the bottom, we have a tetrahedral mesh, composed of 4-faced elements. Tetrahedral meshes are excellent for complex geometries and automatic mesh generation. While they require more cells for the same accuracy as other mesh types, they offer superior flexibility in capturing intricate geometric features.
Now we want to prepare the geometry in Discovery for generating a conformal mesh. So we go to the Prepare tab. Like SpaceClaim, you can see in this software we have a Share tool. We click on Share, and after that click on Complete. Now our geometry is shared, and if we hide the big cylinder, we can see the line, which means the geometries are shared correctly. We show all the geometry again. If you want to unshare the geometry, click on Unshare, and finally click on Complete.
Mesh quality is one of the most critical factors in ensuring accurate and efficient CFD simulations. Poor mesh quality can lead to convergence difficulties, increased computational time, and inaccurate results. In Fluent, several metrics are used to assess mesh quality, with the 3 most important being skewness, aspect ratio, and orthogonality. Let's now discuss one of the most critical mesh quality metrics in CFD, skewness. Skewness essentially measures how close a mesh element is to its ideal shape. For triangular or tetrahedral elements, skewness quantifies how much the element deviates from a perfect equilateral shape, where all sides and angles are equal. For quadrilateral or hexahedral elements, it measures the deviation from a perfect right-angled element. Mathematically, we define skewness using this formula, where we take the difference between the optimal cell size and the actual cell size, then divide by the optimal cell size. This gives us a value between 0 and 1. Looking at our quality scale here, a skewness value of 0 represents a perfect cell with ideal geometry. Values between 0 and 0.25 indicate excellent quality cells. As we move down this scale, the quality decreases. 0.25 to 0.5 is considered good, 0.5 to 0.75 is fair, and 0.75 to 0.9 is poor. Any cell with skewness above 0.9 is considered very poor or potentially degenerate, and these cells often cause simulation failures. On the right side of the slide, you can see visual examples of what we're talking about. Here's an equilateral triangle compared to a highly skewed triangle. Similarly, below we have a perfect equiangular quadrilateral contrasted with a highly skewed quadrilateral. Now, let's examine the practical implications of skewness in our CFD simulations. This slide focuses on how skewness affects our simulation results and the best practices for managing it. Looking at the impact on simulation, there are three key points to understand. First, high skewness can significantly degrade solution accuracy. When cells are highly skewed, the numerical approximations become less accurate, affecting the overall quality of our results. Second, cells with skewness values exceeding 0.95 are particularly problematic. They frequently cause convergence issues, meaning your simulation may struggle to reach a stable solution or might not converge at all. These highly skewed cells are often the first place to look when troubleshooting simulation failures. Third, highly skewed cells reduce the interpolation accuracy between cell centers. Since CFD solvers calculate values at cell centers and then interpolate between them, poor skewness distorts these calculations, leading to inaccurate flow predictions. Moving to best practices, we have several guidelines to follow. As a general rule, keep the maximum skewness below 0.9 for most applications. This threshold helps ensure reasonable stability and accuracy. For more complex flows, such as those involving turbulence, separation, or multiple phases, we need to be even more stringent. In these cases, aim to keep maximum skewness below 0.75 to capture the complex physics accurately. Finally, pay special attention to skewness in critical flow regions, areas where you expect significant gradients or important flow features. These might include boundary layers, regions near walls, inlets, outlets, or areas of particular interest for your specific application. By following these guidelines, you'll significantly improve the reliability and accuracy of your CFD simulations. Remember that mesh quality is often the foundation of successful CFD analysis, and skewness is one of the most critical quality metrics to monitor. Now discuss another important mesh quality metric in CFD, aspect ratio. Mathematically, the aspect ratio formula is quite simple. We divide the length of the longest edge by the length of the shortest edge. Unlike skewness, aspect ratio starts at 1 for an ideal element and increases as the element becomes more stretched. On the right side of the slide, you can see visual examples that clearly illustrate this concept. At the top, we have an equilateral triangle with an aspect ratio of 1 compared to a highly stretched triangle with an aspect ratio of 20. Below, we see a perfect square with an aspect ratio of 1 contrasted with a stretched rectangle that has an aspect ratio of 20. Looking at the quality guidelines, an aspect ratio of 1 represents a perfect cell with no stretching, like an equilateral triangle or a perfect square. Values below 5 are generally considered good for most applications. Aspect ratios between 5 and 20 may be acceptable in certain regions, particularly where the flow is aligned with the stretching. However, values above 20 often become problematic unless they're specially placed in boundary layer regions. It's important to note that unlike some other mesh metrics, high aspect ratio cells can be acceptable or even desirable in certain situations, particularly in boundary layers where the flow gradients are much stronger in one direction than others. In these cases, aspect ratios of 10 to 100 or even higher might be appropriate when properly aligned with the flow. Now let's turn our attention to orthogonality, another essential metric for evaluating mesh quality in computational fluid dynamics. Orthogonality measures how close the angles between adjacent cell faces or edges are to the ideal 90-degree angle. For structured meshes and hexahedral elements, orthogonality quantifies the alignment between the vector connecting adjacent cell centers and the normal vector to the shared face between those cells. Ideally, these vectors should be perfectly aligned. Mathematically, orthogonality can be expressed through the dot product of two vectors: the vector connecting adjacent cell centers, shown as S in our diagram, and the face normal vector, labeled as N in the illustration. Perfect orthogonality occurs when these vectors are parallel, resulting in a value of 1 for their normalized dot product. Looking at the diagram, we can see a visual representation of orthogonality. The vector S connects the centers of adjacent cells, labeled as IP1 and IP2, while N represents the normal vector to the shared face. In practice, we aim for minimum orthogonality values above 0.15, with values below 0.1 often causing simulation problems. The best meshes maintain orthogonality values as close to 1 as possible, particularly in regions where accurate calculation of gradients is critical. I hope this video is helpful for you. To benefit from Mr. CFD's services, including simulation, consultation, and training, visit our website, www.mester-cfd.com. Contact us via info@signmester-cfd.com.